This is a review of our class meeting from Tuesday, April 28th, 2020. It deals with trends in the universe, or universal trends, two universal trends, one of which we've already talked about, and then a way to tie those trends together to consider whether chemical reactions can do work for us or not. All right, so the trends in the universe are, the first one is that a big trend toward lower energy. Things tend to lose energy, and we've talked about that quite a lot as the year has gone by, that chemical reactions most often are exothermic, like burning a match or having a fire in your fireplace, burning gasoline, burning food. All those are exothermic reactions, which means they release energy and move toward a lower energy state. So there's a big trend in the universe toward lower energy. Just to review one that we've done in the class before, you have zinc plus hydrochloric acid, you get zinc chloride plus hydrogen gas. You may remember that when you touch the test tube, it gets very hot, like the day that we made the balloons that exploded in the ceiling. The environment, a reaction container got very hot, which means that heat is released. So that illustrates one of the chemical reactions which loses energy as it occurs. So today I want to introduce you to another trend in the universe, and I'll just go ahead and tell you what that is. And that trend is toward more disorder. If you look around where you are sitting right now, you may notice that your room tends to get more disorderly as time goes by. So an increase in disorder could also be illustrated in this reaction. So if we look at zinc as a solid and hydrochloric acid as being aqueous, over here we would end up with zinc chloride, which is aqueous, means dissolved in water, and hydrogen, which is a gas. So where is there more disorder in this reaction? Well, the gas phase is much more disorderly than the solid or liquid phase, so that would be also illustrating more disorder. Okay, the lower energy, the energy trend is called the enthalpy trend. Enthalpy, you could think of as stored energy. So enthalpy, or heat content, stored energy. The other trend is called entropy. So this disorder in the universe is continually increasing, and things tend to try and move to a lower energy state. So more disorder, entropy; lower energy state, enthalpy. So now I want to show you a little movie that illustrates an endothermic process. And we'll write the chemical equation. Actually, I'll go ahead and do that now. So the chemical equation that he's going to work with is ammonium chloride and barium hydroxide. When they react, you make barium chloride and ammonium hydroxide. This is going to be solid, as is the barium hydroxide. The barium chloride will be aqueous, although there won't be enough water to make it completely dissolve, but you'll see things get wet. And this actually decomposes into ammonia, which is a gas, plus water. So you may remember that earlier in the year we worked with carbonic acid, H2CO3. An example of that would be HCl plus sodium hydrogen carbonate is H2CO3 plus NaCl. But when you did this reaction, it bubbled like crazy. We did it in the lab, and the bubbling is because carbonic acid decomposes into water and carbon dioxide. Ammonium hydroxide is kind of like carbonic acid, where when you make it, it immediately decomposes into ammonia and water. This is ammonia in the gas phase. It smells like Windex window cleaner, except really, really strong. And the water would be liquid. And then to balance this chemical equation, since there are two chlorines here, you'd have to put a 2 over here. That gives you 2 NH4s, so it gives you 2 of these, and that gives you 2 OHs, which is, matches there. And then this 2 just carries down to that. So the things that we're going to be thinking about as we look at this chemical reaction are the ammonia and the water, not the ammonium hydroxide. All right, that all being said, let's take a look at this little YouTube movie which does an experiment that is kind of interesting. All right. And if I just have to find that YouTube movie, I thought I had it set here. But we'll find it real quick. There's your coronavirus homework page, and I posted this movie here.
What I have is some barium hydroxide. Okay, and I'm going to put this into the... In fact, you know what? I'm going to do this in one of the beakers, not that thing, because it's ridiculous. Barium hydroxide, and I've got some ammonium chloride. Now what I'm going to do is mix these together, and hopefully we should see a endothermic reaction. Yes?
It's with the hand stuff.
What hand stuff?
The hand sanitizer.
Oops.
Oh, it just lives on my desk.
Oh.
I was chopping up hearts earlier, and yeah, I need to be not covered in blood. So, what I'm going to do to show how exothermic this is, how much heat this is taking in, I'm going to make this wooden block wet. Okay? Now, you will see why I've done that in a second. So, I'm going to mix these two things together and carefully, I need to break that up a bit. Mix these two things together. Well, hopefully not, because if it's blowing up and giving out...
So they just asked if it was going to be exothermic, and we're hoping not. No, we're hoping it's not exothermic, and it won't be. So notice the ammonium chloride and the barium chloride are both in a solid phase. So, and the beaker's here in a solid phase.
Huge amounts of energy like that, that would be what type of reaction? Exothermic. Now we want to see endothermic, so it's going to be a little bit more subtle. So I mix the barium hydroxide and the ammonium chloride together, and they should start to react.
Does it freeze it?
Well, we should soon see. So they're mixing together. Now can you see how the consistency of that is changing slightly?
I'm going to remind you that at the bottom on this block, you had some water. So let's go back here.
Barium hydroxide. Okay, I'm going to put this into the... In fact, you know what? I'm going to do this in one of the beakers, not that thing, because it's ridiculous. Barium hydroxide, and I've got some ammonium chloride. Now what I'm going to do is mix these together, and hopefully we should see a endothermic reaction. Yes?
It's with the hand stuff.
What hand stuff?
The hand sanitizer.
Oh, it just lives on my desk.
Oh.
I was chopping up hearts earlier, and yeah, I need to be not covered in blood. So, what I'm going to do to show how exothermic this is, how much heat this is taking in, I'm going to make this wooden block wet. Okay? Now,
He said exo, he meant to say endo. Notice the water?
I'm going to mix these two things together, more subtle. So, it's sort of clumping together, because one of the products it's making is
Notice that it's getting wet here.
water in this reaction. And you can see actually that's all gone liquid, and it was all just solid powders. It's not milk, you wouldn't want to drink it. Okay, and you put that in coffee, oh, there'll be problems. Now, one of the products of this, because it's ammonium chloride, is it's giving off ammonia, which smells rather horrible. And I'd forgotten about that, which is why I just breathed the huge load in. That whole sort of horrible, slightly tangy smell in wee is sort of ammonia-like.
Oh, is that what I can smell?
Yeah, that's what you can smell. Unless you wet yourself, that is the best way you can smell. Okay, but also, actually, this is getting actually very cold as it's going along. Okay, now hopefully this.
His joke about wet yourself has to do with urine decomposes and creates ammonia gas when it decomposes. So if you've ever been around a diaper pail that kind of smells bad, kind of a sharp, pungent odor, that's because of the ammonia that's being given off by the diaper pail.
It's getting cold enough. Well, you know I put water on the base there.
Yeah.
Fingers crossed. It's actually frozen the water onto the bottom. Now, this reaction has worked so well. So much energy has had to be taken out of the environment. It's got that water so cold that it's dropped below freezing and frozen onto the bottom. And that is pretty cool. Well, I haven't got. In fact, I have got a filter. I'm an absolute liar. So I can put that there. That is dropping down to. Well, we know it's below what? 0. So
Freezes at 10.
this thermometer is calibrated to -10. It's shot down to -5 by about now, and it's carrying on going.
Will it freeze our fingers?
If you had it on there, yeah, it would start to. In fact, there's actually ice crystals forming on the side
Can I,
on
can
there.
I touch the side? It's
cool.
so cool.
Yeah. No.
All right, so that is the an example of an endothermic process. So let's just review a little bit. If we have two graphs, pull this back over here in the middle, I'd like for you to think about which one of those graphs, this one, or this one, would represent the reaction that we just saw in the video. This is enthalpy. Once again, enthalpy means heat content. And again, enthalpy. And these are time on this axis. This is reactants, products, reactants, products. So which one of these two graphs represents the chemical reaction that we saw? Well, since energy was going in, we would put energy over here. Notice how that's the opposite of the one I mentioned earlier, where energy was released. So energy would go on the left side. So if you're putting energy into something, it's like pushing a rock up a hill. You're going to end with more energy than you began. So at the end, you have more energy than you began. This is called an endothermic process. And this is called an exothermic process. All right, so this lesson today is about endothermic processes and also how they work with the other trend toward more disorder to determine whether reactions are available to do work or not. So if you look at this particular reaction here, see how you've got a solid here and a solid here. This is aqueous, which means dissolved in water. This is gas, which means you know what gases are, and liquids. So which side would have more random motion of molecules? Well, I think you know that solids are much more structurally arranged, and they don't change very much than are things that are dissolved in water or liquids or gases. So you can see that as you go from left to right, the reaction is becoming much more, or the matter is becoming much more disorderly over here. So this reaction actually is driven by the concept of entropy. The reaction occurs because the entropy is increasing. I'm going to divide this video into two parts so that it doesn't get too long. So this is going to be the end of part one, and then I'll come back with part two, which I'll post immediately after part one.